Hello, class. So on this video, we'll continue on section 3.5. In the previous video, we saw an example. We saw how we could find the general solution to this particular non-homogeneous second-order linear ODE with constant coefficients. And so I'm not going to go through it again because we went through it in detail. So what we're going to do now is do another example, and basically following the same process as before, we're going to give a reasoning for how we can, a reasoning for why we would choose a particular solution of a specific form, which we'll see what is going to be. And then with the previous example and this example, it's hopefully enough to convince you of the general algorithm. In general, what do you want your choice for y sub p to be given what we have? Okay, so that's going to be the idea. These two examples are building to the general form we're going to choose for the particular solution. Okay, so let's go ahead and try to find the general solution for this ODE. So find the general solution to y double prime minus 3y prime minus 4y equals 2 times sine of x. Okay? So this is second order linear with constant coefficients, but it's not homogeneous, right? Because what's on the right-hand side, or whatever is not being multiplied by a derivative of y, is not equal to 0, right? It's, in this case, 2 times sine of x. But by theorem 1, again, we know what is the process. We first find the general solution to the homogeneous case. And again, we know how to do this, right? Just look at the characteristic polynomial, right? You can read it off immediately from here. So P of R for us is going to be R squared. Sorry, it doesn't look like an R. So it's going to be R squared minus 3R minus 4, right? And then we set it equal to 0 to find the roots. So R squared minus 3R minus 4 equals 0. And again, if you can factor it directly, try to factor it. If you can't, you can always use the quadratic formula. So let's see. I'm going to try to see if it factors. I think it does, as R minus 4 and R plus 1. Let me double check if that works. So R squared plus R minus 4R, that's negative 3R minus 4. Yeah, this works. Right? So what are our roots? Our roots are R1 equals 4 and R2 equals negative 1. Now that we have the roots, just go back to the slides in the previous video or memorize them, or just, or eventually you just memorize them because you use them. But we get that the general solution is y of x equals e to the c1 e to the 4x plus c2 e to the negative x. So again, this we know how to do easily, right? The problem is how to find a particular solution. So just as before, we're going to leave this as an aside just to use later when we want to find the general solution for the whole ODE at the end. So I'm going to separate this. And now we're going to go again to the process of finding a particular solution. Okay. So let me rewrite what the ODE is. So we have it here. So it's y double prime minus 3y prime minus 4y equals 2 times sine of x. And then as before, what we're going to do is we're going to see what assumptions are reasonable for us to put on our particular solution y sub p. So what assumptions should we put on this function? Okay. And again, what we're going to do is inspect the ODE and see what, based on the ODE, what is reasonable to use. Okay. So we're looking for a function y sub p that after taking its second derivative, subtracting 3 times its first derivative, and subtracting 4 times itself, we get 2 times sine of x. So basically, it would be ideal if you had a function whose second derivative involves terms of sine, whose first derivative involves terms of sine, and whose y, so itself involves terms of sine of x, right? Why? The goal is because we want to have sine x on 2 times sine x on the right-hand side. So after we take all of these derivatives and simplify, we want to have an expression involving sine x on the left-hand side. Okay, so that's my reasoning into what we're doing right now. I want to have something that after I take derivatives, as it looks on the left-hand side, I get something that has sine of x. Okay? Well, then one possible choice is this. Right? This is definitely a possible choice for a particular solution, for a form of the particular solution. Now, notice one thing here. I always include a parameter, in this case, a constant a. So actually, let me write that a is a constant to me. So every time I write these capital letters A, B, C, no matter how many I write, they're going to be constants, but let me make it precise. Now, notice that here, I'm always including a constant, a. Why? For the reason that I want to be able to have a parameter that I can control. It's the same reason why in the previous example, for our choice of the particular solution, we used a linear polynomial where the coefficient for x and the constant were undetermined, right? Hence the name undetermined coefficients, right? Why? Because leaving those constants undetermined gives us, in one way to say it is, gives us some wiggle room for us to choose constants that work. So choose values of a and b that make the differential equation true. If I weren't to choose a and b like this and just choose a and b immediately, like give them names like 2 and 5, then 100%, like 99.9% of the time, that polynomial is not going to be a solution. So instead, you leave yourself degrees of freedom in the sense that you leave a and b undetermined and you determine them later by plugging it into the ODE, just like we did in this example. Right? So that's the reason why I always leave a constant wherever I can. So again, it gives me degrees of freedom to choose a constant that works for this differential equation. And again, that's why this method is the method of undetermined coefficients, because we have coefficients that are undetermined, but they're determined later after we plug it into the ODE, just as we did in the previous example. Okay. Now, as I mentioned, going back to this problem, a sine of x is a possible form because when we take its second derivative, we get something that's a constant times sine of x. Right? When we multiply y, which in y sub p, which is a sine of x times -4, again, all we get is a constant times sine x. So it's something that looks like this, potentially. Now, what is the problem with this choice? The problem with letting y sub p just be a sine of x is that when we take the first derivative of y sub p like this, what do we get? We get a times cosine x. Now that's a problem. Why? Because looking at this ODE, right? So looking to sine x, looking at this ODE, and let's say we plug in this particular solution, what are we going to get? So let's plug in is yp equals a sine x. So I guess we have to find the derivatives, right? So we found the first derivative. Let's write down the second derivative beside it. So y sub p double prime would be negative a sine x. So let's plug all of this in to the ODE. So what do we get? Y double prime is negative a sine x negative 3. Oh, no, yeah. No. And then minus 3 times y prime, which is a cosine x, and then minus 4y, right, which is a sine x. And hopefully this is equal to 2 sine of x. And now after I simplify, you're going to see why this is a problem. So let's just combine all like terms. So I'm going to combine all terms that have sine and all terms that have cosine. So those are the two functions that I see. So if I combine the terms with sine, I see negative 4a minus a times sine. And if I combine the ones with cosine, I see negative 3, negative 3a. Negative 3a times cosine of x equals 2 sine x, right? That's what we want. We want it to be equal. Now, hopefully you can see that there is a problem here. We have a cosine on the left-hand side, but there is no cosine on the right-hand side. The only way we can get rid of this cosine on the left-hand side is if a is 0. Just looking at the expression, that's the only way cosine disappears. But if a is 0, the original function is just 0, because the original choice for y sub p is a times sine of x. And that's a problem, right? We don't want to guess 0, because we know 0 is not going to be a solution, right? Because this is non-homogeneous. So we're kind of stuck. This choice of y sub p equals a sine x doesn't work, because again, after we plug everything in, we have a term involving cosine, which we don't want, right? Because we only have sines on the right-hand side, and there's no way to get rid of this unless a equals 0, which means our original choice was 0 to begin with. So that's a problem. So this one doesn't work. So let's go back to the drawing board. Now, again, the only thing that we know for sure is that a reasonable assumption, or no, not a reasonable assumption, but that we want a function such that when we take its second derivative, its first derivative, and have its function itself, right, and then combine all of these terms, I should hopefully get something that's equal to 2 times sine of x. Now, we know that the sine function satisfies that when we take derivatives, we get sine again, but the problem here is that when we take the first derivative of sine, we get cosine. So how can we modify maybe this guess of a form for the particular solution so that we can potentially cancel the cosine? Again, here we can't cancel it, but maybe if we modify it, we can actually cancel it. So let's try this. Let's try y sub p equals a sine x. And I'm going to modify it by adding b cosine x. Now, why am I doing this? I'm doing this because if I add a term with cosine in my original guess, then when I plug it into the ODE, right, what's going to happen is my term that has cosine is probably going to involve, a's and b's. So it might look like some constant times a plus some constant times b times cosine. Now this is good because now we can solve for a and b without them having to be 0 in a way that we can cancel the cosine term. And again, this is possible. It's possible to get a term like this if we start with a guess that looks like this. This is not the only way to do it, but it's one way to do it. Again, right now we don't know what the right course of action is, so we're just taking guesses that make some sort of sense. So again, in summary, if we do this, we can get a form after we plug it into the ODE. Let me write it like that. After we plug this into the ODE, we can get the cosine form or the cosine term factor or term, we can get the cosine term to look like, some constant, so some multiple of A plus some multiple of B times cosine. And again, this is good because that means we can potentially cancel the cosine term without having to have A and B equal to 0. And we can potentially cancel the cosine term without having A and B equal to 0. And again, we don't want this because if A and B equals 0, our original guess is just 0. Okay? So that's why something like this, modifying our original guess by adding a cosine term, is a good idea. Okay? Because it gives us a way to cancel the cosine term after we plug it into the ODE without having our original guess being 0. So what we're going to do is just go ahead and try it. So we need two things, right? Well, we need to know what the first derivative and second derivative are. So let's find them. So first derivative is going to be A times cosine x minus B sine x. Then the second derivative is going to be minus A sine x minus B cosine x. So what we're going to do is plug this into the ODE and see if we can solve for A and B in a way that makes the ODE true. So as a reminder, the ODE is, so y double prime minus 3y prime minus 4y equals 2 sine x. So let's go ahead and plug it in. So y double prime is negative A sine x minus B cosine x. Then minus 3y prime, so minus 3 times y prime, which is A cosine x. Actually, I don't know why I wrote parentheses here. We don't really need them. So A cosine x minus B sine x. And then we need minus 4y. So minus 4y. Y was A sine x plus B cosine x. So minus 4. A sine x plus B cosine x. Right? And all this should be equal to 2 sine x. So as before, we're going to combine all the terms involving sine and all the terms involving cosine and see what we get. So let me do that in a different color, maybe dark blue. So I see for sine, I see a negative A. I see a negative 3 times negative B. So that's plus 3B. So I see a plus 3B. I see a minus 4A. And that's it, right? So I see a minus A plus 3B and a minus 4A. Now let's see what we find for cosine. So for cosine, I see a minus B. I see a minus 3 times A, so a minus 3A. And I see minus 4B. Right, so from here. And again, this should be equal to 2 sine x. Now let's simplify. So let's combine all the a's and b that we can combine. So this becomes negative a minus 4a, that's minus 5a plus 3b sine x, plus I have minus b minus 4b, so that's minus 5b minus 3a cosine x equals 2 sine x. And now you see, as we explained before, why this is better. Now, it's possible for us to have choices for A and B that make this term with cosine go away without having to have A and B equal to 0. And again, we can't have A and B equal to 0 because then our original guess would just be, y equals 0, which we know doesn't work because our differential equation is non-homogeneous. So let's see what equations we get. So the first equation I already talked about. We need whatever's multiplying the cosine to be 0 in order for that cosine term to go away. So I get minus 5b minus 3a has to be equal to 0. Now I have two unknowns, so hopefully I can get two equations in the two unknowns to solve for them. So now let's look at the sine term. This here, if we want it to be equal to whatever's on the right-hand side, the coefficient multiplying sine has to be equal to the coefficient multiplying sine on the other side, right? So we have negative 5a plus 3b has to be equal to 2. Okay. And again, this would make this equation true because it would make the cosine term go away, and it would make the coefficient of sine on the left-hand side match the coefficient of sine on the right-hand side. So two equations, two unknowns. Let's go ahead and solve. What we're going to do is solve for either variable on the first equation and then plug it into the second. So from the first equation, I can solve, let's say, for a. So add 5b to both sides, divide by negative 3 to get negative 5 over 3b. And I'm going to plug this into equation 2. So we have negative 5 times a, which is negative 5 over 3b, plus 3b has to be equal to 2. So let's simplify. So we get 25 over 3b plus 3b equals 2. So let's combine them. We need a common denominator, which would be 3. So this becomes 25 over 3b plus 9 over 3b equals 2. And now we can combine them since they have the same denominator. We get 34 over 3b equals 2. Then multiply by 3, divide by 34. And we get that b equals 6 over 34, which I think we can at least divide by 2. 3 over 17. No, that's not. Yeah, that works. So know what b is. Now we can just plug this in back to the equation for a to solve for a. So a is going to be equal to negative 5 over 3 times b, 3 over 17. So let's see, the 3's cancel. So this is just negative 5 over 17. So what does this mean? Our particular solution then would be y sub p equals a times cosine, right? Is that how no, a times sine, I think is how I wrote it. Or let me just double check. Yeah, so make sure that you put in the coefficients after you found them in the right place. So this is, yeah, a times sine, okay. So a is negative 5 over 17. So negative 5 over 17 sine x plus b times cosine, 3 over 17 cosine x. And that's a particular solution. And again, this works by construction. However, if you see, there's a little bit more algebra involved in this problem compared to the other one. So this is something that if you were doing this in the second exam and you found your particular solution, if you have extra time, it would definitely be nice to actually plug this back into the ODE and make sure that it is in fact a solution. So you can always do that. You can plug this back into the ODE and make sure that it is in fact a solution. If you're 100% confident with your algebra, then this is the correct solution, assuming that your algebra is right, because it works by construction, right? We decided a form for y sub p, and then we determined the coefficients a and b that make this a solution. So it's a solution by construction. So then what is the general solution for the whole ODE? is the sum of the general solution for the homogeneous case and this particular solution that we found. So the homogeneous case had what solution? So 4 and -1 for the exponents. 4 and -1. So right, this comes from the homogeneous case plus our particular solution, which is -5/17 sine x plus 3/17 cosine x. And this is the general solution. What is the interval of definition? Well, it's the common interval of definition of the general solution of the homogeneous case and the particular solution. As we know, this always has interval of definition -infinity to infinity. So as always, or as I said in the previous video, what's going to determine the interval of definition is going to be the interval of definition of the particular solution. If you look back at the original ODE, there's no restrictions on A and B, on X and Y. And this is always going to be the case because it's linear with constant coefficients. Unless, of course, we have a square root on the other side or anything like that. So as long as the function on the right-hand side doesn't have, square roots, or we're not dividing, anything like that, then it's always going to be the case that there are no restrictions on X for our solutions, right? So there are no restrictions on X in that front. Also, sine and cosine are defined everywhere, so there's no restrictions on the domain. That means that this works on all real numbers. And that's the general solution. So in the next video, now that we've done 2 examples and saw what the particular solutions or the forms of the particular solutions were, in the next video, I'm going to give you, okay, this is the general way we're going to approach this.